Okay, you should have in your handouts this periodic table looking thing. It's called the Pauli scale, periodic trends in elements electronegativity. This is perhaps one of the most important words in the reactivity of elements in chemical reactions, because it defines where reactions take place and what elements are most reactive and least reactive, the electronegativity. And it's defined as an element's attraction for electron cloud. In the periodic trends, what we see is from left to right on the periodic chart an increasing electronegativity. In series, electronegativity, I'll use En, save space, En increases with increasing atomic number. In groups, electronegativity decreases with increasing atomic number. There's the rules. Let's see if I can get all this on one page. Here, there, yeah. Electronegativity is the influence of the nucleus of an element and how its attraction is to its electron cloud. And the larger the number, the greater the attraction. So Linus Pauling came up with this table in terms of a number that more or less the attractive force associated with the nucleus against the electron cloud. And so you can see it starts with 1 on lithium, 1.5, 2, 2.5, 3, 3.5, 4, and so forth. In series, as you look, you'll see the numbers are increasing in atomic number. But in groups, you see it decreases. Well, the reason it decreases in groups is because the rings that you're adding places the valence and the electrons further and further away from the nucleus. So this is a large distance of the valence electrons from the nucleus. And so these would have lower electronegativities where you have very large radii, but would have high electronegativities if you have a small radii. And so that will play a big part in how bonds break and make and behave throughout the study in our work on chemical bonding. Now, he also had in his work definition of what a nonpolar covalent would be. If the two bonding elements, if you took like carbon and chloride were bonded, you'd have a 3 and a 2.5. Take the difference in those two and 1.5. Well, that 1.5 would fall within this and it would be called a polar covalent bond. Some of the cloud would be shifted, and we'll describe this again in more detail. But if you had a carbon-carbon and you took the difference in those two, it would be 0. So if you're less than 0.5 between the two bonding elements, it's a covalent bond. And if you were like sodium and chloride we talked earlier about, you have 3 minus 0.9, it would be greater than 1.6 in the difference in electronegativity. And so you could classify the bond as highly ionic or polar covalent, and polar covalence will translate into easy break, and we'll later, which is a later topic, or non-polar covalence which is very difficult to break. So this is a very important table in terms of understanding the nature of the covalent and types of bonds that we are using, especially as they apply to reactivity.